De Broglie said, electrons and other particles act like waves and have a wavelength. This was shown to be true by Davison and Germer. Davison and Germer showed that electrons can diffract. That's a wave property. As we've seen, the way Davison and Germer produced a diffraction pattern was by firing an electron beam from a filament toward a nickel crystal. The beam scattered only in specific angles and didn't scatter off in other angles. Thomson did a similar experiment where he fired an electron beam from an electron gun toward a circular slit in a metal foil. He found that the beam of electrons split off into specific directions, producing these rings on a back screen. In both experiments, there were locations where we found lots of electrons, shown by the beams and the rings. Those are called maxima, and there were locations where we didn't find any electrons. Those are called minima. Maxima and minima are formed when two waves interfere constructively and destructively. That means electrons are waves, right? But what do we really mean that electrons are waves? Well, all we can say so far is that they diffract. But isn't there something more to a wave besides the ability to diffract? For example, what does the amplitude of the wave represent? This is not a question that de Broglie had an answer to. These questions were eventually answered by Erwin Schrödinger and Max Born. Schrödinger explained in a famous paper how to write down something called the wave function of the electron. The wave function will actually change based on certain facts like whether the electron is bound to an atom or whether it's free. Let's take a simple circumstance like this. An electron is trapped somewhere in the bottom of a box of length L. It's just a two-dimensional box, and maybe the electron is here, or maybe somewhere else. We don't know where exactly the electron is. All we know is it's somewhere at the bottom of this box. If we assume a pretty simple situation, like the particle, the electron, is trapped at the bottom of the box, and the electron is in its lowest energy level, then here's what the equation looks like that allows us to calculate the wave function psi. This symbol psi represents the wave function. L is the length of the box, and x is just some position along the box. So here's what the equation says. You can calculate a value of psi, the wave function, at different positions along the box. At this position, there's some value of psi. At this position, there's a value of psi. At this other position, a value of psi. But what exactly is psi, the wave function? The answer is a little strange. If you take psi and you square it, then what you now have is the probability of finding the electron at that position. Now, I'm not going to work out a full example because doing so actually requires calculus and integration. But let's say here's the wave function equation, the equation that lets us calculate psi, the wave function, at different positions. And of course, we're dealing with an electron trapped somewhere at the bottom of this two-dimensional box. Let's say the length of the box is really small, 0.10 nanometers. And we want to know what's the likelihood that the electron is 0.06 nanometers from the left wall. The way that you answer the question is you plug in a value for x, for position, plug it into this equation right here, 0.06 nanometers, calculate the value of psi, the wave function, when the value of x is 0.06 nanometers, and then square that answer to get psi squared. What you'll now have will be pretty close to the probability of finding the electron at a position of 0.06 nanometers from the left wall when you look inside of the box.